Now, in this lecture series, we shall learn that how we can design the structural steel foot over bridges, that are quite commonly used in Australia to, we can say, go from one point to another. So here you can see the GR Design and Construct. So all the pictures belong to them and all the projects have been done by them. So these pictures are available free of cost on their website, and that is why we are discussing about that. So let us say, first of all, if you're talking about this particular project of them, that is Mormac Development, the Point Estate. So here you can see that they have given a 25-meter truss and 40-meter truss. They have adopted the painting for the marine environment so that the corrosion does not happen, and that is also DDA compliant. So if we look into the pictures, so this is the first picture that they have shared. So we can see here that the foot over bridge of the truss that is like prepared. That is a simple truss kind of arrangement. And if we are talking about the bridge itself, that is made in the cold form sections. So here you can see that how they have made a beam, and on top of those beams they have installed the C purlins, the cold form purlins, and to transfer the load from this point to the edges they have made another truss. So usually what happens is that the point of support here, the one that we can see here, that is a little bit lower as compared to the bridge. So that is why they have raised this level. So we can see from this particular picture here. Yeah. So this point of support is at the lower level, but the bridge is made at the upper level. So that is why we do need that truss arrangement here, so that we can install the we can say battens or uh, deck on the top. So this here is a one more picture. So here you can see that this is the concrete edge on which this foot over bridge is getting supported, and this is the main foot over bridge on which they have installed the simple timber deck. So this is again one more picture where they are lifting this with the help of the crane. So this picture is very clear and gives us a very clear idea of how the actual construction happened when we're talking about the foot over bridges. So if we're talking about any other country, let us say if we're talking about the Middle East, Dubai, or we can say Abu Dhabi, or Asian countries like India, China, or American countries also, this is usually made in the hot roll sections only. But as due to the we can say Australian we can say climatic conditions or the point of view, so that is why this access here, that is a deck on the top, that is made in the cold form sections itself. We can zoom into the picture also. So this here we can see that how they have made the we can say C purlins, and they have fixed the C purlins with the help of these are known as the cleat or plates, and they have fixed all of these C purlins with the help of these two bolt, and they look like of 16 mm diameter. They are usually of either 5.8 grade or 4.6 grade or 8.8 grade also. And here also you can see that how they have made the truss, and on the truss basically they have ensured that this member does not have any excessive bending, and all the load gets converted into the actual force that is partially transferred to this point and partially transferred to this point. So we can model this foot over bridge also in our calculations and check that how they have made. So let us just have an idea of what exactly are the dimensions of this. So here you can see that let us suppose this Mr. XYZ is of height 1.8 meter. So here we can see that the height of this truss, it is approximately in the range of 2 meters. So yeah, so let us say it is in the range of 2 meters, and the span, I think it is in the range of 40 meters. So we won't go as long as 40 meters for the first trial itself. We can opt for a little bit of lesser span. Let us say we can adopt for 25-meter span of foot over bridge. On height, we can reduce it to 1.8 meter. Now, how we can, ensure that the height is decided. So in this project, what they have done is that they have not applied any kind of railing here on the top. Railing, obviously, they have applied railing in the form of these, we can say, tertiary members here. Here also you can see the handrail, but we don't need any additional handrail on the top of this. So that is how the height is also decided, and it has to be ensured that as a simple basic truss analysis principle, the more the height, the lesser shall be the sizes of these members. So that is the because the more the height, the smoother shall be the angle, or it shall be in the range of 45 degrees itself. So what we can do is that, so let us assume that for our problem case, we do have like input that, okay, we do need a span of, let us say, 30 meters. And let us say the height of this truss can be maximum 2 meters. So what we can do is that we can, divide this whole braces and ensure that this segment is also in the range of 2 meters, so that this angle becomes 45 degree. So after that, let us suppose I'm not drawing the exact dimensions, but there are like two different principles of the truss arrangement. One principle is that either, let us say these are the vertical members. So one principle is that we can make a truss like this. But I personally do not prefer this kind of truss arrangement. The reason here is that wherever this member is in, let us say, in tension, this member which becomes very, we can say, low in size, because steel is very good in tension. But this member here, this member is the one that is facing the compression. So what will happen is that for aesthetical reason, in many of the cases, we do need to have the same sizes for these members. So what will happen is that the tension member, that shall be under design, and the compression member, obviously, that shall be designed as per the compression forces that is coming. But in tension member, the utilization ratio as per the structural steel design shall be very low. So that is why it is always recommended that in these kind of cases, what we can do is that we can have this kind of arrangement. So what will happen here is that all the members shall be in tension, and we very well know that steel is very good in tension. So by this, we can ensure that all the members that we are having are in tension, and these are the one that shall be carrying primarily the, we can say, vertical forces. And on the bottom, we can say this is basically our member, but there shall be a very, very low value of the bending moment. And by making this kind of arrangement, where, we are having, let us say, all the members as the tension members itself, or we can say as the truss members itself, there shall be very less value of the bending moment also. So what will happen is that uh, we do have to make the bottom members also. Let us say we draw the bottom plan. So and what happens in many of the countries is that we can simply, have secondary members here, and then we can add another, we can say, secondary member, and on the top of that, what they usually do is that they put the deck sheet, and on the top of that they do the concreting. But in Australia it is not the case. What we usually do here is that, like I have shown you in the picture also, let us say these are the structural steel members. So what we usually do is that we put our member around here. These are the simple horizontal bending member, and on the top of that, what we usually do is that we do put our C purlins as per the bending moment requirement. And from here, like from this particular horizontal member, we do ensure that all the, members, or all the bending moment that is coming from the deck sheet on the top. Let us say any human is, walking on this. So all those, bending moments, that shall simply be transferred from the purlins, and then purlin to this particular beam, and then from this particular beam to this particular member, and from this particular member to the main horizontal, we can say, vertical structural steel members. So that is a basic cross section that is usually adopted in Australia. So this height is usually in the range of, let us say, in our case, the one that we are going to model, that is approximately 2 meters. So we can assume that, let us say, this height is approximately 0.5 meters. And this width, that is, let us say, approximately 3 meters. So what we can do is that dead load, we know that shall be the, we can say, self weight plus the weight of the, we can say, deck on the top, or timber deck. So usually we do install the timber deck on the top of this. the one that you can see from the picture of the project that we were discussing earlier. So here you can see that all of these are the simple timber members, but on the bottom of that you can see the C purlins. So that is the basic, mechanism that is followed, and that also includes the self weight of the handrail also that we can, that we are putting on the top. And here you can see this is basically the splicing connection here. So what they have done is that they have fabricated this into 1, 2, and 3 parts. And those 3 parts are joined with the help of these bolts or splicing bolts or within the splicing plates that we can see clearly here. So that is why here you can see that there is a little bit of gap between the two foot over bridges. So that is like first concept. Obviously, we know we cannot fabricate a single span of this foot over bridge from one point to another. We have to like make a splicing connection in between. So that point is well understood. Second point that we do need to understand here is that the span needs to be divided judicially. So let us say in our case, we do have a span of 30 meters. So either what we can do is that we can, make a single 30-meter span with double members here. Or what we can do is that as of now, we can just make a single 30-meter foot over bridge. And as a second trial that you can do at your end also, you can make separate 3 structural models of 10-meter span. So that is also, both of these practices are correct. Either modeling a single 30-meter span and at the site ensuring that there are these 2 members, or the second principle is that we can make 3 separate structural design models of 10-meter span. But what we should be doing is that we should be modeling a single 30-meter span so that, on the if we can do the maximum, obviously you can do with the lesser span also. So here you can see that first of all, we can start with designing the C purlin members. So let us assume the span is approximately 2 meters and the live load on the top that we can assume it is as 500 kg per meter square. So, and the purlins are like simply supported here. So it is not that all the purlins are separate. Both of these options can be done. Like here you can see that on all of these members here, you can see these plates on which these purlins are fixed. So either there may be a joint here also, and the purlins may be continuous also. The purlins may be spliced here also. It all depends on the structural design calculations that you are doing. So here also you can see that how they have fabricated the splicing system here. So we can open the ETAP software, and what we can do to save time in this case is that instead of starting the raw model again and again, what we can do is that you can click on the option view settings from the model file and then left click on OK. So in here, what we can do is that the earlier example in which we have designed the members with the cold form mezzanine, you can just simply click on that. So what will happen is that all the load cases and all the load combination that shall simply be, we can say, imported here. So as of now, just to check, we can click on blank here and then left click on OK. We can go to the load patterns. So here you can see that all the names and all the exact load combinations have been directly imported. And we can go to the load combinations also. So like in the earlier example where we were saying that we have to do the process again and again, in this example, we can just simply skip that by this kind of application. And we can go to the material properties also to check. So here also you can see that all the material properties have been imported from the we can say sample file that we have discussed in the earlier lecture series. So after that, we can click on the edit stories and grid systems, and instead of we can say these multiple stories, we can delete story 2, 3, and 4, delete story and delete existing structure at story. Here we can select the height as 2 meters and left click on refresh view and then left click on OK and click on modify show grid system. So here what we can do is that we can either make the multiple grids with the spacing of 2 meters up to 30 meters. So we can click on the grid A. This is basically the grid along X. So we do need the grid along X. And here we can select X as 2 meters. display grid data spacing. Here we can select all of these spacings as 2, and Y we can select here again as, let us say, 1, and here we can again select the spacing as 2. So we can left click on OK, click on refresh view, and then left click on OK again. So we have not modeled the complete thing, but we have just modeled a single grid system so that we can just simply replicate what we are making here. So we can go to the define section properties and frame sections. So here you can see that those sections are also like simply imported from what we had done in the earlier lecture. So yeah, there's one more thing. We can go to the edit stories and grid system, and we can add a story also for the uh, like the level where we were having that tech. So here we can select the height as 0.5, and here we can select the height as 2 meters. Click on refresh view, then left click on OK, refresh view, and then left click on OK again. So we can go to the define section properties and frame section. So in the example, we had seen that we were talking about the box section. So all of these sections are the box sections here. So although this can be made with the help of the C channels also, or we can say eye girders also, like in some of the pictures that they have shared in their projects, they have adopted the eye girder also. But if we are going ahead with the eye girder, then we do not need this truss arrangement. Both of these principles are separate. Let me just show you the picture first of the eye girder. So here you can see that what they have done here is that they have simply made the eye girder, but they have not adopted the truss system. So both of these systems are completely different from each other. Either we can make a system where we can just simply add a steel plate girder of, let us say, 15 meter span. We can add the end stiffeners, we can add the intermediate stiffeners also. These are known as ITS, that is intermediate transfer stiffeners. So wherever there is a very high shear force possibility, we do add these shear stiffeners. So if we are making a cross section, let us say this is the eye girder, we do add these stiffeners on both the sides of the, or we can say, web. So what will happen is that the example, or we can say calculation, is very simple. The bending moment here for this particular scenario shall be something like this, and the shear force diagram, that shall be something like this. So that can be done with the help of the simple hand calculations also, as per AS 4100, which is guiding us on how to design the steel plate girders. So on the top of this, we do not need any kind of, we can say, truss arrangement. We just need to install the, we can say, handrail as per our, we can say, Australia National Construction Code. The height is usually kept as 1100 mm. That is like the minimum statutory height, and this is required as per US also, Europe also, Australia also. So that is the another concept. So let me just elaborate the basics structural system principles. First principle is that we can adopt the steel plate girders. Let us say we do install one steel plate girder on the extreme left of the foot overbridge, one steel plate girder on the extreme right. We can tie these foot overbridges with the help of these members. These are also the hot rolled structural steel members. And on the top of that, we can just simply install our timber on deck. The second option is the one that we had discussed here, that we can have this kind of, we can say, arrangement where we do have the members here also, structural steel members, and these are also the structural steel members. And usually, as you know, we do need to take care of the wind load also. So that is why all of these members are usually, we can say, SHS, that is square hollow section, or RHS. So what we can do is that we can design the arrangement with the help of this option also, and this option also. But the only disadvantage here is that wherever the span is very less, let us say this span is only in the range of 10 meters, let us say. So in that case, it is always recommended that we can make a simple eye girder. But if the span here is, let us say, 30 meters or 40 meters, in that case, it is not recommended that we do go for that very steel plate girder, because the depth requirement itself shall be in the range of 1800 mm or 1500 mm. So that shall unnecessarily increase the cost also, and that shall look aesthetically also, that shall not look okay. So that is why wherever the span is large, we do adopt this truss kind of system for foot over bridges, and wherever the span is less, let us say in the range of 10 meters, we just simply make the steel eye girders from left hand to right hand, and then just hand over the project to the client. So that is the basic concept. So what we can do is that in our project, if we are talking about the 30-meter span, so we can go to the define section properties and frame section. In here, we can click on import new properties, and then we can click on the box and tube section. In here, we can select Australia, New Zealand, and we do need to select the C350 grade. That is the grade for the box section. We can click on add new material, and in here we do know that the code guiding us regarding the box section is basically either they are available in C250, C350 or C450. So we can proceed with C350 grade that is already added here. So in here we do get these members here, that is 100 by 100, 150 by 150 or 200 by 200. Let us say we proceed with this 250 by 250 by 6, and then 200 by 200 by 6, and then 150 by 150 by 6, and then 100 by 100 by 6. We can add 125 by 125 by 6 also. Why I'm taking 6 mm is that because we do need minimum of 5 mm thickness of weld. So if we are talking about 5 mm thickness of weld, then we cannot take as such 3 mm member or 4 mm member. So we can left click on OK here. We can again click on import new properties, square hollow section. In here we are getting the option only of steel tube. And if required, like we can have rectangular hollow section also. So 250 by 150 by 6 is the rectangular hollow section, 200 by 100 by 6, and 150 by 100 by 6 also is a rectangular hollow section. So we can left click on OK here, and what we can do is that we can manually design the C purlins with the help of Expecta design software. So that also we shall be doing in the further lectures. But as of now, we can just start with draw, beam, column, and brace subjects. In here, let us say if you want to model the members. So let us say in the first trial, we proceed with 250 by 250 by 6. And momentarily shall be continuous as we are talking about the bottommost member here. So this is basically the bottom member that we have modeled. You can just right click here so that the mouse or the cursor becomes free, and then again left click here from this point to this point. So right now, we have made a simple, what we can say is the bottom truss member. And then after that, we can make the verticals also. So similarly, we can make a vertical also from this point to this point. Here, so we can make again the vertical members here also. Similarly, vertical members can be drawn on this grid also. As I said that we do have an option that whether we can tie the members on the bottom also or not. So here we can see that there are no as such horizontal member running along the bottom chord. we do have this diagonal member here. So what we can do is that instead of 250 by 250 by 6, we can select 200 by 100 by 6 member here, and then ensure that both of these, trusses are tied to each other. Tying two trusses is very important, especially in the areas where there is a high, we can say, seismic force probability. So in that case, we do need to ensure that the system is tied as much as possible so that it shall behave as a single unit at time of the extreme earthquakes. So we can adopt 150 by 100 by 6 member here from this point, and if we wanted to snap to the midpoint here, we can go to the draw snap options. We can click on the line ends and midpoints and perpendicular projections and lines and frames option. Line ends and midpoints, lines and frames, perpendicular objection, left click on apply and close. And then we can select just simply the midpoint here from this point to this point. Again, we can select the midpoint from here to here. Same exercises can be done here. And then here also. So now, we have just simply modeled a frame member. And if we want to go with the truss arrangement also, so what we can do is that we can adopt 200 by 200 by 6 member, and we can just simply make this arrangement like this. Now either we can join to this member or to this member, but for structural stability, it is always better to join this point to this point here. So now we have modeled the vertical members also, diagonal members also, horizontal members also, and the main supporting members also. Now in the next lecture, what we can see here is that what should be the size of these C purlins that we do need to install on the top. So that we do need to check in the X Factor design software.